Okay? There used to be 2, 1 and 2, and now there's 3, right? So that's nice. That was convenient. Okay, how about hydrogens? How many hydrogens are on the left side?
8.
We have a 2 that we added in front of this now, so there's 3 times 2, 6, plus 2 more. So we have 8. Okay? Did we do oxygens already?
Yeah.
Are you sure? No, I don't think we did. 2 times 2 is 4 plus 3. Correct? So this is supposed to be how many now? 7. All right, so we added up all these after we made the change. Now what do we do to balance this side? A 2 in front of this? Because that would help the hydrogens, because there's no hydrogens in this thing, right? So if we put a 2 in front of this, now how many hydrogens are we going to have? 8, right? 2 times 2, 4, 5. Is that right?
This is awesome. Do it more than twice.
2 H2, HC2H3O2.
I did 2
Oh, here's the
questions.
problem. I didn't
These
put
are
a
my
2
two
right there. So we
answers.
have 4 carbons here. No, we've got 4, 5. We have 5 altogether. All right, do we have 5 carbons on the left now? 4 and 5. We do. Okay. How many oxygens do we have on the left? 7. So looky there. What did we do? We balanced it, right? Same number of hydrogens on both sides, carbons, sodiums, and oxygen on both sides. That was a hard one, huh? But all we had to do was just keep trying, going back and forth. And we can always start over if we don't get it. We can just erase all the numbers that we put in front and just start over, right? Okay, but we got it. We got it. Now this is an important equation for us because we're working our way towards doing an experiment, right? And this is the experiment that we're going to perform. Do you guys know anything about any of these chemicals? Okay, this is called sodium carbonate, and it's very similar to baking soda. This is vinegar, that's right. And if you mix vinegar with baking soda, it bubbles, right? And the reason it bubbles is because this stuff breaks down into carbon dioxide and water. And carbon dioxide is a gas, so it bubbles. So what we do is we take a balloon. This is a balloon, not a very good drawn one, but there's a balloon. Inside, it's a flat balloon, it's not blown up yet, right? Does that make sense? Inside the balloon, we put the sodium carbonate. Okay? And then we put that balloon on top of a flask. So before we do that, we put the vinegar into the flask. And then we seal the balloon on top of the, balloon like that, on top of the flask. And then we dump the balloon into the vinegar. And then what's going to happen? The balloon inflates, and so it looks something like this.
Are we gonna do it?
But then you want to be able to seal it fast enough.
Dada, are we gonna do
Yes,
it today?
Not today, no. We're aiming for, hopefully, we'll see as soon as we can do it. But before we do it, we have to learn how to do stoichiometry well. Because, look at this. There's a ratio. How many vinegars do you need for every sodium carbonate? Yeah. 2 vinegars for every 1 sodium carbonate. Yeah, twice as much vinegar as sodium carbonate. So when we blow up the balloon, after it's blown up, we can measure the outside of the balloon all the way around with a string, and we can tell how much carbon dioxide we got by the size of the balloon. Bigger balloon, more what?
Carbon dioxide.
Carbon dioxide. All right? You can also tell from this type of an experiment, if you didn't put enough vinegar in, then some of the powder will still be on the bottom. Does that make sense? Some of the powder will still be on the bottom if you didn't put enough vinegar in.
What if you never put enough baking soda?
If you don't put enough baking soda in, there will only be vinegar left and water, but the balloon won't be very big, right? So we're going to do an experiment where we see the size of the balloon based on the amount of either vinegar or sodium carbonate that we add. Okay? So that's what we're working towards, trying to be able to do this experiment. Now, let's ask you a question about this experiment then. Okay? Here's a question that you're going to use stoichiometry to answer. Now, I told you that setting up the problem is extremely important, almost more important than knowing how to use your calculator. Okay? So, I want to make sure that you know how to set up a problem when provided. So here's the question. If I have 0.3 moles of Na2CO3, how many moles of HC2H3O2 do I need? What? Oh, you need the periodic table? Well, here's the periodic tables if you want them. Take one and hand it around. I don't think you actually need one to answer this question, though.
I need one over here.
What you do need is scratch paper.
Guys, this is useless.
And then
Atoms.
How much a mole is for each atom, but it doesn't tell you how many.
okay, grab a pen, grab a paper, take one and pass it down. Got a pen? Don't write on the periodic table because we'll run out of space and we'll be ruined.
David, that's it because I had that stuff. Look, I am a noble gas. This is the one that I got last time.
Everybody else need a paper?
And a pink one, pass it down.
You go. Grab a piece of paper there. All right. Now, let's see how you guys set up this problem. All right? What's the, write somewhere else on. What's the first thing we do? Equal sign. Equal sign. What's the next thing we do? The next thing we do is we write a line. Who else needs pens?
I need a hard surface.
Okay, we write an equal sign and then we draw a line. What goes to the right of the equal sign? What goes to the right here of the equal sign?
Moles of HC2, H3O2.
That's right, because that's what the question is. Moles of HC2H3O2. So I'm going to write here, moles of HC2H3O2. All right, moles of that stuff. That's what we're after. What did they tell us about? Top left, we write down what they told us about. What did they tell us about?
How?
You have 0.3 moles of Na2CO3.
Good. 0.3 moles of sodium carbonate. 0.3 moles of Na2CO3. All right, very good. What units have to go down here? You need moles of what here? HC2 moles of vinegar. Here we're starting with moles of sodium carbonate, baking soda, right? Excuse me. So, we need to get rid of, let me move this over a little bit here. .3 moles of Na2CO3. We need to get rid of moles of sodium carbonate, Na2CO3. Moles of Na2CO3 need to go down there. How did I know those needed to go down there? So they can cancel out. That's right. Then what's going to go up here? Moles of vinegar, that HC2H3O2. So I'm going to write here moles of HC2H3O2. All right? Now, what's the ratio of moles of vinegar to moles of sodium carbonate?
2 moles of vinegar.
Where did we get that information? Where does it say that?
Because it says there's a 2 in front of H.
What do we call these numbers in front of these? The stoichiometry. The equation, this is a special land here, the land of the equation. Right up in here is the land of the equation. And you can go to the land of the equation and get the power of the stoichiometry. Right? And once you have the power of the stoichiometry, then you can solve these kinds of problems. Right? All right, so what is the ratio of acid, or the vinegar, to the sodium carbonate? 2 to 1. There's 2 moles of this for every 1 mole of that. Now, does everybody see where that was at? Where did I get that from, Emma? Here. How did I know there was 2 moles of HC2H3O2 and 1 mole of sodium carbonate? Some point where I knew, how I knew that it was supposed to be a 2, and how I knew that was supposed to be a 1. Because right here, 2, CH3H3O2, and just 1, NH2CO3. So that's where I got 2 to 1, right? Very good. So it was the stoichiometry of the equation that allowed me to know the ratio here. So then I can find my answer now, right? Because moles of sodium carbonate cancel out, and I'm left in moles of HC2H3O2, right? So what's the answer? What values do I put in my computer, my calculator? Times 2. 0.3 times 2. Times 2 and divide by 1. So put it in your calculator, and that's your ticket out the door for the day.
Okay.
Show me your calculator. Oh, there's one right there on the table.
I got it. I don't have a calculator.
Go sit by Emma's shirt. Way to go.
Wait.
Try again.